So let me start. It's a great pleasure for me to introduce our today's speaker, Professor Bazaliy from the University of South Carolina, United States. A few words about his biography and scientific career. Yaroslav is originally from Donetsk, Ukraine. After finishing high school, he moved to and started studies at Moscow Physics and Technology Institute, MFTI. He obtained his master's degree in 1988, then worked at Kapitsa Institute for Physics problems and obtained a kind of PhD degree or candidate now degree in 1992. After that, shortly after that, he moved to United States and worked there. Among his places where he worked as a researcher are Argonne National Laboratory, IBM Research Center. He also worked shortly in Netherlands, about 1 year, at Leiden University. And since 2006, he is working as professor at the University of South Carolina. He, although he worked in many places as a scientist, he is tightly bound to Ukraine, and he has several distinctions and awards from National Academy of Sciences of Ukraine. He also obtained a habilitation degree in 2009 from National Academy of Sciences, Ukraine. Also, he has several awards and distinctions from United States. He has an SF Career Award and Rising Star Award from the University of South Carolina. He is very active in research expertise, in grant expertise, and as a reviewer for many journals. He is also a member of several boards, international boards, both in Ukraine and in the United States. And importantly, last year, Yaroslav came with an initiative to our Kharkiv University to give lectures on voluntary basis, and we were happy to involve him as invited lecturer in master course solid state physics at our department at the Faculty of Physics and Technology. We deeply appreciate his initiative and the lectures that he gave to our students. Currently, he is also involved as in the course of quantum information theory, kind of mentorship of students, and he has several ideas how to develop this for mentorship for Kharkiv University and for Kyiv University, Taras Shevchenko University. So there are some ideas around how to team up with professors all over the world in mentoring Ukrainian students, because currently we are facing these challenges that students are lacking communication with professors due to war, due to ongoing online courses since the pandemic situation in 2020 until now. So if you are willing to contribute and to team up with Yaroslav or us, so please free to contact us at any time. So it would be great to brainstorm and come with some ideas of mentorship of students. So with that, I would like to pass my microphone to Yaroslav, and please, Yaroslav, Professor Bazaliy, the floor is yours.
Thank you, Andrei. Thank you for this nice introduction. And my suggestion is that after the talk is finished, if there is somebody here who will be interested to talk about students in Ukraine and what can be done, let's just stay for another 15 minutes and have a short conversation. Maybe there are some people who have this problems in their universities and who think about it. That would be nice. So I'll start sharing. I'm not going to do the full screen, so you will see this menus and stuff, but that will help me because I will see some of your faces. So if it's okay, we'll do it this way.
Yeah, that's all right.
Okay, so we'll talk about spin currents, and hopefully it will be a little bit entertaining because some of their properties are unusual and they challenge our notions that were instilled in us from the early time when we're starting to learn physics. Yes, so the plan is very simple. There will be a pedagogical introduction into the spin currents in metal and ferromagnetic structures, then short break, then we'll discuss the giant magnetic resistance phenomena just to practice, and then there will be the substance of the talk. There's two unconventional examples. So we're going to talk about metallic materials, and they can be either normal metals or ferromagnetic metals. But in both situations, the electrons, which are shown here as blue dots, that carry their spins, which are shown as blue arrows, they just simply move. And so these itinerant electrons can go from one contact all the way through the material to the other contact. So everywhere we will use the shorthand N for the normal metal and the shorthand F for the ferromagnetic metal. When people realized that spins are not always disordered, they understood that currents in a metal can have two possible natures. You transport charge, and that's the normal electric current, and you transport spin as well, and that's the spin current. So here are some of the examples which we would like to discuss before we go forward. First example, the first picture shows the normal electric current where there is a same amount of spins up and spins down, and they all go to the same direction. So there is electric current, but the spin is not transported because of this balance between up and down spins. There can be a partially spin polarized current. Here in this cartoon, we have two spins up, one spin down. So obviously there is charge transport, but in addition, there is a transport of spin because more spin up is going from left to right. You can have fully polarized spin, fully polarized current. So this is a charge current. Everything goes to the same direction, but all the spins are also parallel. So the amount of spin transported is simply a spin times the value of particle current. And finally, this is something that can be new, the pure spin current. In this situation, you have spins up going to the left and spins down going to the right. And the statement is that because there's equal numbers of charges going to left and right, there is no electric current. But at the same time, there is a spin current which is going from right to left. And so the statement is that this spin, which is down and goes to the right, transports the same current as this spin up going to the left. And the way to see it is if you imagine here a reservoir on the left, where all these particles end up eventually, then you count how many spins are, what is the change of spin in this reservoir. So this guy brings one extra spin, but the fact that there is this guy means that one spin was removed. The one down spin was removed, one up spin was added, the total change is two up spins. And that's how you understand that the second electron actually produces the same spin current. We all know that it's easy to create electric current with batteries and stuff, but we have to talk about the ways to create pure spin current, because electric field doesn't do anything to it. So all through this talk, we're going to consider a very specific limit of electron motion in these materials. We will assume that momentum relaxation time is much smaller than the spin relaxation time. And the cartoon here tries to show what it means. So the orange line is the trajectory of an electron. And where it has kinks, that's where the momentum scattering happens. So the direction changes here, and then here, and then here, and so on. The point is that the average time between collisions which change the direction is tau p, but tau s is the time between collisions that flip the spin. On this picture, there's only one such collision, and you see that the spin actually is up before and it's down after the collision. So you have many, many collisions which change the direction before you have this one collision that changes the spin. And after that, for a long time, the electron moves with the other direction of spin. The mean free path is defined in the usual way. It's V Fermi times the mean free motion time. But in addition, there is this new parameter, the spin diffusion length. And what it tells me is how far will electrons that starts here go before the spin flips. So what is the average distance from here to here? You see that electron can do strange trajectories between these 2 points. And the character of motion from the beginning to the moment when you have first spin flip is diffusive. It's a random walk. So the distance here is measured by how far you diffuse in a time equal to tau s. And that's the usual formula which describes it. So if tau s is much larger than tau p, you see that lambda s is much larger than the mean free path. That's what we will use. And now that's an important slide. We will talk about equilibration of the general non-equilibrium state of electrons to their equilibrium state. So suppose you don't have any currents, everything is uniform in a piece of material, and what you do is you prepare electrons in some arbitrary non-equilibrium state. And you wait until they get into equilibrium. And what we know what this equilibrium will be. It's going to be a filled Fermi surface. Let's assume that we are in the we're talking about a good metal. The temperature at which we do experiments is much lower than the Fermi temperature, so you get a nice sharp Fermi surface, and everything is filled twice in the states inside the Fermi surface, and everything is empty above the Fermi surface. And there is a Fermi energy or chemical potential, which is shown here by the black line. So everything is filled inside the band below the Fermi potential. Now, the statement which is important for us is that the approach to this final equilibrium is going to go in 2 stages. There will be one first rapid stage. The time of this first stage is going to be of the order of tau p. And then there will be the second stage, which will be much slower. And the second stage characteristic time is tau s. So in between, there is a period of time between tau p and tau s when you have a partial equilibrium. Electrons collided many times with impurities, with each other, with phonons, whatnot, and their direction of motion is completely randomized. But their spins didn't have time to flip many times. They are essentially the same as they started. And in this intermediate state, the good description for what you will see is the picture on the very right. So there will be 2 surfaces. And inside of the blue one, the occupation is double. So every state is occupied by spins with two directions. It's a spin singlet. And in between the inner and outer surface, there is a single occupation. And all the spins inside this region have the same direction. And if you look at that from the point of view of energy, you see that there is an energy which characterizes the inner surface. That's the red line here. And inside, everything is doubly occupied. And outside, and there is another energy characterizing the outer surface. And the way you can imagine the picture on the right is this. You fill everything below the red line with spins in one direction. You fill everything below the blue line with spins in the opposite direction. The direction can be whatever. What's important is that they are opposite. And then automatically below the red line, everything is doubly occupied. And between the two lines, everything is single occupied. And above the blue line, everything is empty. So it's important that in this intermediate equilibrium, everything in between the two surfaces has the same spin direction. And you can ask, why does it happen? And at this point, I will just say that there is an argument why this should be this way. So you cannot have single occupation, but random directions of spins over there. If you have that, then there will be a fast relaxation in the time of the order of tau p, which will simply decrease the distance between blue, this energy distance between blue and red line, and make all the spins parallel to some direction. And by the way, if you have questions, please don't hesitate. We don't have too many people now, so it's a good atmosphere to ask questions and stop me.
Short question.
Yes.
Where should those uncompensated spin point?
It depends on the starting conditions.
Spontaneously.
Sorry?
Spontaneously, like in ferromagnetism. Okay.
It's not like in ferromagnetism. It's, well, in some sense, yes, but my statement is that you prepare the initial very non-equilibrium state. Electrons are all over the place. Their spins point wherever you want, and you wait and you see what happens. And then the direction here will depend on how you start. So the total spin does not change on the time of the order of tau p, because there are no processes which flip spin that are so fast. And so the total spin with which you start and this total spin in this intermediate equilibrium are the same. But the distribution of spins over k points is different as a result of this partial relaxation. Does that make sense?
Yeah, okay. No external field. Okay.
No external field. At this stage, no spin flips have actually happened, but you still can have a situation when two spins that were in different k vectors, different momenta, get into the same. They are scattered somewhere with impurities, and as a result, they acquire the same momentum. And their spins were different, but when they go into this single momentum state, they form a singlet. That's not forbidden if their spins were not exactly opposite in the beginning. And this is a process which is important, but let's just believe me that that's what's going to happen. But it's a fine point which deserves discussion, not within this seminar. So there's two chemical potentials, one for spin ups and the other for spin downs, are shown here again, and the distance between them is called the spin potential. And one of them is called mu up, and the other is called mu down. And the average, the middle part, will be called simply the mu, the average potential. The previous slide was for a normal matter. There, the direction of spin in the partial equilibrium was arbitrarily determined by initial conditions. In a ferromagnet, the situation is very, very similar, but there's one important distinction. There is a magnetization M, and after you have the after you have the equilibrium, all the spins are either parallel to M or anti-parallel to M. It doesn't make sense to consider spins which are at an angle to M. This is the relaxation which, if you come from the perspective of Bloch equations and magnetic resonance, is the T2 time, the phase coherence relaxation, which is also very, very short. So there is other important difference here. The left side is the uniform, the equilibrium situation in a ferromagnet. So if you have equilibrium ferromagnet, then we will talk about it in the Stoner model. There are two bands, upper band where the spin downs live, the spins are opposite to magnetization, and the lower band where spins up live. There is a splitting between the band, the Stoner gap, and the larger is the gap, the stronger is the ferromagnet, and the more is the difference between the equilibrium number of spin ups and equilibrium number of spin downs. And this difference determines how much spin polarized in equilibrium is the ferromagnet. So this is the equilibrium state of a ferromagnet. There is a region where there are both up and downs, but there's also a region where there are only up spins. And so there are more up spins than down spins, and everything is magnetized. When you can prepare a non-equilibrium state and wait for partial equilibrium. And in this partial equilibrium, the picture is what you see on the right. It's very similar to the left, except now the blue circle is smaller and the white circle is larger. There is more spin ups than usually in equilibrium and less spin downs than usually in equilibrium. And that's this partial equilibrium or partial non-equilibrium state, which will relax during the time tau s to the equilibrium on the left. Again, you can introduce the mu s, which is the energy difference between the level for up spins and level for down spins, and the average electric potential. So here, the hallmark of non-equilibrium state is mu s being non-zero, not the different number of electrons in up and down pools. Now we will talk about the transport, the currents in this situation. And we will use this two-current model, and we will talk about the diffusive transport. So the two-current model uses what I said before on the slide, that you can look at all that and say that there is separate gas of electrons with spin up, and there is a separate gas of electrons with spin down. When spins flip, the particles transform from being in one gas to being in the other gas. But this happens very rarely, so we can, for a while, think about the two gases as being separate. And so we want to simply use our intuition about diffusion. We learn about diffusion at some point in a very simplistic picture, and we'll learn the Fick's law that diffusion is proportional to the gradient of concentration. And here there is a twist to that. There are two possibilities to induce diffusive current here. The first one is a gradient of concentration. The second one is electric field. Both of them are very natural to us. Electric field is what it induces diffusive currents in normal metals when we use electricity from the wall plug. And the gradient of concentration is what we understand very well for diffusion in gases. But here, both sources of motion are present. Both of them can generate the motion of electrons and therefore the motion of charges and maybe the average motion of spins as well. So in our picture, we simply say that, okay, we'll look at the two spins separately. There is a gas of spin ups, there is a gas of spin downs, and let's see what both things do to them. Both sources of motion, both forces, do to them separately. Before I go into that, there is one important point. Then, if we talk about the transport of electric current in a normal metal, where spins are totally randomized, that means you're talking about this full equilibrium of spins in normal metal when there is equal numbers of particles with up and down spins. And therefore, there cannot be a gradient of concentration because that would violate electron neutrality, because you have to maintain the number of charges, negative charges of electron being equal to the number of positive charge of ions. When you have two gases up and down, then each of them can change their concentration so that the sum of the concentration is still the same and neutrality is maintained. So this is why you have both possibilities. There is electric field, and there is also a concentration gradient. The concentration gradients exist, but they are related to each other because neutrality has to hold. So now, if you look back into your high school or whatever early college textbook, you will see that you can unite the chemical potential that tells you about the concentration and the electric potential that tells you about electric field into one electrochemical potential simply by adding them like it is shown here. And then the two influences of two forces are combined and they are expressed by just one gradient of this electrochemical potential. And that has to do with the Einstein relation between mobility and diffusion. But again, this is not rocket science. If you remember that, great. If you don't remember, just believe me. That's how it happens. So these are two equations in the red box at the bottom that we want to consider. But we would like to, before we actually consider how we solve them and what is the solution, I'd like to talk about a transformation that is very useful to do to them. And there is this transformation which I already discussed. There's two formulas on the right. We define the average potential, electric potential, as the average of mu up and mu down. And the spin potential is a difference between them. So that's a spin polarization that you have. And then you can also do the same trick with the currents. If you take the sum of up and down currents, then you will get the full transport current of electrons, and that will be your electric current. There is a slight notation thing which I want to discuss. Electric current is proportional to the particle current, which is given here by Jn, times the electric charge. Electric charge is negative, and that has a potential for a lot of confusion. So it's very often easier to talk about particle current rather than electric current. That's why I specifically separated. And this J up and J down, they're going to be particle currents. How many spin up particles go from left to right? So the dimension of JE is the amperes, but the dimensions of everything else is number of particles per area per second. So you define these two currents, electric current, and this is a spin current, the difference of J up minus J down. And then you can transform those two equations on the previous slide for separate channels up and down into the equations for Jn and Js, the normal particle, the particle current and the spin current. And here's what you get after you do that properly. So both of the currents are induced by the gradients of electric potential, or the average electrochemical potential, and the gradient of the spin potential. And there is an important parameter, P, the polarization of conductivities, defined here above. So in the normal metal, there is no difference between spin up and spin down conductivities. They are the same. P is equal to 0. When you go to a ferromagnet, then there is a finite P. And the larger is P, the more is conductivity polarized. And if you look at this equation for a minute, you will see that in a metal where P is equal to 0, they are uncoupled. Electric current is produced by the gradient of electric potential. Spin current is produced by the gradient of the spin potential. In the ferromagnet, they are coupled by the term with the P. Okay. Now, what do we want to do? We want to solve first a very pedagogical problem, and that will help us later. So the problem we want to solve is here on the right. We want to see what happens if you pump electric current through the boundary between the ferromagnet and the normal metal. What happens when you pump it through the boundary between two normal metals is very familiar to us. So the blue line shown here, that's the chemical potential mu E, electric potential. And so these two metals, on the left and on the right, can have different conductivities. But electric current is given by sigma times gradient mu E. And so the gradients of mu E will be different here and here. At the boundary, we assume that the boundary is very transparent. So that leads to boundary conditions that mu, or the mu's are the same on both sides. And there's no jump of mu. If there was jump, that would be some contribution from tunneling then. And so there are just two lines that are straight lines. They're straight because electric current has to be the same on both sides. And they have to come to the same point. And that's a picture of how chemical potential changes. We want to understand how it happens here. So what are the equations that we want to solve? We will work in the two current picture with mu up and mu down to start with. And here's a picture of the transport. The black box is a small volume of the material. There are spin-ups electrons entering this small box, and some of them are leaving. Same for spin down. And inside of the box, there is a rare process of spin flip, which is described by the time tau s, which converts ups to downs. So we want to describe this process of transport and relaxation by equations. And these are the equations. The number, the concentration time derivative inside the box is proportional, is equal to the divergence of current with the same spin. And on the right, there is a term describing the relaxation. The relaxation becomes larger and larger as you are further and further from equilibrium, with n up minus n down becoming larger and larger. And there is a tau s in the denominator that is characterizing the relaxation speed. So if there wasn't relaxation, we would have just simply two conserved currents for up and down spins. If there is a relaxation, the two equations are coupled by term with tau s. And what we will do, we will trade the concentrations for the derivatives of concentrations, which you see here and here, to derivatives of the chemical potential mu up and mu down, and they are related by the densities of states. So you can do that, and you get an equations for mu up and mu down. The exact form of them is not very important, at least for this first pass of discussion. And this slide is extra. It simply tells you that you can, instead of talking about the mu up and mu down potential, you can reformulate everything in terms of mu s and mu electrical, just like we did slide before. And the exact form of it is not very important, but it's important that you can do it. So this problem of the current passing through the ferromagnet/normal metal boundary was considered a long time ago. This is a reference to it. And in this PRL, it was considered by solving the two current model. They calculated mu up and mu down as a function of distance, the boundaries at x equal to 0. And when they solved the equations above, here's what they found. The potentials, mu up and mu down, are continuous on the boundary. That's because of the assumption of the transparent boundary. Near the boundary, they become unequal. Far away from the boundary, they are the same. This mu s potential, the spin potential, is largest at the boundary, and then it drops down both ways. So far away, everything is spin independent, just a normal current going through the materials. But at the boundary, the spin starts to play the role. There is a spin accumulation developed at the boundary, and then it decays deep into both materials. So far away here, there is a constant current, of course, everywhere, because it's a one-dimensional problem. And the gradient of mu, of both mu's, they have the same gradients, and they give you this constant current. Same goes for here. So you can draw two black lines. One black line is a continuation of this identical blue and red lines far on the left. The other black line is a continuation of identical blue and red lines far on the right. And when you continue the black lines, you see that they do not go to the same point. And what it tells you is that there is an extra voltage developed on the boundary. If you want to find the voltage between far away on the left and far away on the right, you will have to take into account the ohmic voltage from the current going through the bulk material. In addition, you will have to add this boundary voltage Vs. And so they calculated the Vs and got a formula that was an influential paper. What we want to do now is we want to look at this same picture from the point of view of the spin potential and the spin current.
Excuse me.
Go ahead.
Yeah, it's interesting. Could you give some simple explanation of Vs? Maybe
my explanation would be this: that what is voltage in all this situation? Well, it's not an explanation, but an alternative point of view. Let's say, suppose you just have a piece of metal and you pass a current. There is voltage, there is current. It's a diffusive metal. You know that there is a production of heat, which is V times I. So there are these relaxation processes which transform electric energy into heat, and that's how you develop voltage. So here you have extra relaxation processes. The spins flip and go from up to down. And together with this extra relaxation processes, you observe extra voltage. And that sort of looks very consistent. The more relaxation you have, the more voltage you need to pass the same current because you produce more heat. It's not an explanation, but it's a different view. And several slides further, several slides we're going to talk about third explanation or the third way to think about this Vs, which is probably the most useful. Okay, so let's think about how mu s and the spin current Js depend on the distance from the boundary. These are the two results of calculations. If you solve the differential equations together with boundary conditions of transparent interface, that's what you will get. Let's start with the spin current. The spin current is something in the ferromagnet on the left, and it relaxes to zero in the normal metal. That's very natural. The ferromagnet polarizes spins. So when you move, on average, everything with electric current, you move more up spins than down spins. And so there will be partial spin polarization of the current that we discussed in the first slide. And so in the bulk ferromagnet, certain spin currents always accompanies electric current, and it's determined by the parameter P. In the normal metal, there is no reason for spin current. So in the bulk, there isn't. But there is an injection. The spin current comes from the interface, and it has some inertia. It goes into the normal metal. And for a while, there is spin current in a normal metal, but then the relaxation kills it. The distance on which it happens is the so-called spin diffusion, is the same spin diffusion lengths that we have discussed qualitatively before. The spin diffusion lengths are different in normal metal and the ferromagnet because they are different materials with different diffusion coefficients, different number of impurities. So there can be different characteristic lengths on the left and on the right, but they are both spin diffusion lengths. Now let's look at this equation for the spin current expressed in terms of the gradient of spin potential and electric potential. And let's look at the picture, the result of calculation for mu_s. This result is that you develop a certain mu_s, it's largest at the boundary, and then it decays. These are actually exponents. It decays exponentially, and the decay length is the same, the spin diffusion length in both materials. So let's
interrupt you.
Yeah.
What processes are responsible for the spin flips in normal metal?
You have magnetic impurities, maybe.
No, you have magnetic impurities in normal metal too.
Maybe you have spin-orbit interaction.
Thank you.
So the microscopic part is interesting, and maybe there are situations where it's very important, but we assume that there is a window where just describing everything by tau s is good enough to discuss it. Okay, so let's look at this equation. Let's look at it in the normal metal. In the normal metal, P, the conductivity polarization is 0, so the spin current is created by the gradient of mu_s with a minus. The gradient of mu_s is pushing the spins to the right, and yes, there is a current flow into the right. It's a positive current, and it dies because the gradient of the spin of mu_s is dying as well. Now, what about here? Here, the gradient of mu_s exists only near the boundary. Far away, there is no gradient. We look at this in this formula. P now is non-zero. Far away from the boundary, this term is 0, but that term exists, and so we have this constant spin current determined by gradient of mu_e, which is determined in turn by the electric current. Closer to the boundary, there is a gradient which pushes spins to the left, and therefore it decreases the result of the second term. And so, yes, the spin current goes down even before you get to the boundary. So the spin current starts to feel that there will be a boundary earlier. It goes down, but it still has some juice to inject spins into the normal metal. That's the picture that I want to convey at this point. And so with this picture, there is a wonderful and very useful way to think about the extra voltage. The picture is this. Let's again look at the second equation. This is the previous slide showed the equation for spin current. This slide shows the equation for the electric current or particle current. Now it's created by the gradient of electric potential, and if you are in a ferromagnet, then it's additionally created by the gradient of the spin potential. When you look at this equation, you can think about this term in the red circle as an effective electromotive force, a small battery in addition to what electric potential is doing for you. And you can think about this extra voltage as the result of the fact that you inserted this effective battery into the circuit. And this was discovered or pointed out by Rajba in 2002, and then rediscovered by many other people. And so if you take this equation and you integrate it along the coordinate of the wire from point A to point B, between those 2 points, you measure the voltage V. Then you integrate it, you move some terms to the left, some to the right, and then you get this integral equation. The first part is electric current divided by the local sigma conductivity. And that's essentially the ohmic part. That is I times resistance. That's the resistance of the ferromagnetic part and the resistance of normal part. All that is taken into account in this term. And then in addition, you will have this from integrated the gradient, because when you integrate the gradient along x, you get the result. It's difference of mu s. And that is equal to the voltage that you measured between points A and B. So if point A is far away in the region where mu s drops down to 0, like this picture shows, then it's this extra voltage is simply P times mu s of 0 divided by twice electric charge. And that's very usual, because when you measure voltages, you actually, you have your voltmeter somewhere in your, not inside your measurement apparatus, but somewhere outside. So point A is basically always very far from the boundary. And that's what you measure. This formula, it's not an answer, it's a relation, because nobody tells you what mu s of 0 is. You have to solve the equations to find it. But if you solve them, then that's going to be the relations it holds. And that's the most important relation for this whole talk, I'd say. Just want to point out that this additional voltage is always positive. It always increases the voltage, or if you think about it, this extra voltage can be perceived as extra resistance of the boundary. This extra resistance is always positive. It doesn't matter whether you pass a current from ferromagnet to a normal metal or from a normal metal to a ferromagnet. You will always get extra boundary resistance from spin relaxation. The pictures try to show that the spin accumulation in these two cases is opposite. Here, spin accumulation is going to be positive, and here, spin accumulation is going to be negative. But when you integrate, the order is also different until the result is the same. You have a question?
Yes, I just thinking about layered heterostructure. So if you have
coming soon.
Okay.
So before we go to layered heterostructures, short break. Rajba's name was mentioned. He did a lot of work in this area, besides all the other work for which he is mentioned. And so what I want to advertise is his very interesting memoirs, which were also published 21 years ago. In the Journal of Superconductivity, there was a conference where he was an invited speaker, and the organizers asked him to write it. It's a very interesting piece. If you search on the internet, you can even find the translation, but it's very well written in English, actually. And it conveys a lot of atmosphere of the 1940s, 1950s. The red box shows that his view was actually that there was by the end of the 50s, he perceived the situation, at least in Kiev, as a decay of scientific potential, and mostly, the good scientists being forced out for different reasons. And contrasts with what we sort of could think about it, but I do recommend reading this. It's a very interesting view on this whole situation of the mid-20th century in physics in Ukraine, and done by a person who has inside knowledge, but also spent a lot of time in the West at the point when he was writing it. So he could sort of write about it in a way that we appreciate now more than a long time ago. So yeah, Rashba is still alive, so he's very old, but very active. So let's go to giant magnetoresistance. This is an application of what we were doing. Let's consider two boundaries between ferromagnets and normal metals. The normal metal is white inside. The two ferromagnets are bluish outside, and we consider the two arrangements. On the left, the magnetizations are in the opposite directions. On the right, the magnetizations are in the same directions. The top two pictures show what happens when the distance between the boundaries, L, is much larger than the spin diffusion length. And then everything dies out before you can, there is an intermediate region here where everything is in complete equilibrium. And so the left boundary doesn't have any influence on the right boundary and vice versa. The black line here is a spin potential μs, just like on the previous slide, calculated by solving the equations. And so there is a picture for an anti-parallel situation. And for a parallel situation, you shouldn't be surprised, because we already learned that if you pass there is an electric current flowing from left to right. So we already learned that there is if you have a current flowing from left to right, then here's the spin accumulation is positive, here's the spin accumulation is negative. It's consistent with what we see here, because now the spin accumulation is positive, but it's negative with respect to the direction of the actual magnetization. That's what matters. So at this point, every boundary introduces its own Vs, extra resistance or extra voltage, into the problem. But the additional voltage is the same here and here. It's just twice the voltage on each of the boundaries. Interesting things happen when you make the distance between the boundaries shorter, comparable or smaller than the spin diffusion length. Then what you see by solving the equation is that spin accumulations here go up, and spin accumulations here for the parallel state go down. And so now these voltages, they're still determined by spin accumulation. It's a sum of spin accumulation here plus spin accumulation here multiplied by P divided by 2E. The formula that we derived applies always, except that now spin accumulation is larger here and smaller here. And that's why, starting from something, you increase the resistance here and you decrease the resistance here. That's how it comes out from your calculation and the universal relation. So you can ask, well, is there a way to understand it more intuitively? And I'd like to advertise a way, which I really like, because that's the way I understood it at some point. You can actually reformulate all those equations governing the diffusive transport in terms of mechanical equations. And these mechanical equations, they look this way. You look at this picture and you imagine that the black line is an elastic rope. So this elastic rope has weight, and normally it would like to lie on the table, the surface of X, of the X coordinate. But whenever you pass electric current, in the mechanical analogy, that's equivalent to producing the red force acting at the boundary, nowhere else, just at the boundary, and lifting the rope from the ground. And the more current you pass, the more red force you produce, and the larger is the height to which you lift the rope. The rope is elastic, so if you pull it here, it starts pulling the other parts of the rope from the ground, but it cannot pull the whole infinite rope. It only can pull something close to the point where you apply the force. And here you apply the mechanical analogy tells you that you apply forces pointing into different directions. Of course, depends on the direction of the current that you pass and the order whether it goes from N to F or to F to N. So these forces are applied in the opposite direction, and if the points where they are applied are far away from each other, then the rope in between still lays on the table, nothing happens here, and all the action happens in the vicinity of the two application points. When you make the distance between the force points closer, like here and here, you see what happens in mechanical analogy. Here the force essentially doubles, and you can lift more of the rope, and the displacement, up displacement, becomes larger. Here the forces act in the opposite direction. They cancel each other through the elasticity of the rope that is tightened in between them. And so that's why there is no action in the parallel situation. So if you train your brain to think about this elastic rope, then many results of solving the partial differential equations will become quite obvious. In particular, this one. Okay, you can read it in the 2020 Cranial Journal of Physics issue. That was an anniversary for Sergei Mikhailovich Ryabchenko issue, and this paper is published there. Also, there is an archive which is in English and is a little longer, but maybe more descriptive. So now we can start and talk about the two examples in the remaining 10 minutes. This is the first example. It has to do with pure spin current. Remember, we talked that it's easy to create electric current, but it's kind of not easy to create a pure spin current. Here's how people do it. Imagine a normal metal, shown here by white, ferromagnet shown by blue, and an electric current passed through the ferromagnet into the normal metal, then back again, completing the circuit. As the electric current goes, it is accompanied by spin current in the ferromagnet, just as we discussed. For the whole duration, there will be an injection of spins. You will create non-equilibrium spin potential just under the injection point. And then we ask, well, what happens to the spins? In the normal metal, spins do not care about electric potential and electric current. Remember, the equations are decoupled. So they will start diffusing from here equally well to the left and to the right. This is shown here on the picture. There will be spin currents flowing to the left and to the right. In terms of electric currents, the left and the right are very different. The left is where the electric current can go and complete the circuit. The right is a dangling wire or a dead end. Electric current cannot go there because it has nowhere to continue. So you can be sure, the argument is, that there is no electric current on the right, and therefore, but there is a spin current because of the diffusion of spins. So there must be a pure spin current there. That's the idea. And that was used in this wonderful paper even earlier than the first by Johnson and Silsby, the Johnson and Silsby experiment. The whole experiment is shown at the top. The left part is what we discussed on the previous slide. Let's look at the right part. The right part is, there are two contacts, the ferromagnetic contact and the normal contact. So schematically, it's shown here. There is a spin current injected from here. It goes from left to right, and it decays, but there is some spin current reaching the ferromagnetic contact, and even some spin current reaching the normal contact. So here, this is shown by more spin current on the left, a little bit less spin current. This injection produces some spin accumulation, so there is mu s right under the contact with the ferromagnet. And then by applying the same logic, you see that the same universal relation is at work. There is no electric current flowing here, and yet there is a voltage, the same V determined by spin-related voltage, determined by how much spin is accumulated right under the contact. So that's they discovered it. They gave their argument in a certain situation why this should be the answer, but it was given for a narrow type of situation than in the Rashba formulation, but the answer is the same. And they measured this voltage. They actually measured this voltage. And for them, it was a way to measure P, the spin polarization in the ferromagnet. And the beauty of that is that it doesn't really matter where you put this contact, where you put the yellow metal contact, because all the voltage is created in the ferromagnet over here. There's no current here. No matter where you put this contact, the result will be the same. There is a lot of freedom to do it. It doesn't matter how thick this ferromagnet is, as long as it's thicker than the mean free path, than the spin diffusion length. I apologize. So here is my example, however. Everything is very clear when the ferromagnetic contact is narrow, a column. But imagine you prepared a wide contact. You don't have fabrication capabilities to make it very narrow, so you sputter the wide contact and you measure the voltage and you do two experiments. In one case, you contact your voltmeter here. In the other case, you contact your voltmeter here. According to Johnson and Silsby formula, you should have the same voltage. But if you try to apply the Johnson and Silsby formula, this relation, then you can ask, well, I know that spins are propagating from left to right here in the normal metal. So there is more spin accumulation here, of course, and then because of relaxation, there is less spin accumulation here. So mu s here and mu s here will be different. So which one should I substitute into the formula? And the idea we had when we started thinking about it was that there must be some correct average of those spin accumulations, and you find it, and that's what you have to substitute into this formula. However, the result was very, very different. So when you think about this, you can actually prove a mathematical theorem that if you have a heterostructure with ferromagnetic parts and normal parts, and the conductivity polarization P is space dependent, then there is this cross product, a vector product of gradient of P and gradient of spin accumulation, and it's equal to the curl of electric current. It should be equal to the curl of electric current. In other words, the theorem tells you that if this cross product is non-zero, then the electric current should be non-zero, because the curl of zero current would definitely. Our structure has exactly that property. It has two parts, and so there is a delta function gradient of P at the boundary. It jumps, and you can think about it as a gradient concentration on boundary. So there should be a current, but there can't be any current because it's a dead end. How could electric current go into the dead end? The resolution of this seeming paradox is that there is a current, but it's a circular current. It's all contained into this dead end wire, but it doesn't have to go outside of the dead end because it circulates. The way you understand this current qualitatively is this. You have large spin accumulation here, And so this effective EMF is large here. And as you go along the boundary, the EMF becomes smaller. So here the EMF is 0. And you have sort of a situation with distributed EMF concentrated on the left, no EMF on the right. And then it's very natural to have a closed circuit with EMF, which pumps the current around it. And it's a circular current. It starts and closes on itself. And we tried to think about it in a more precise way, quantitative. The first, what you do is you double the picture, you reflect your real device, and then you get a very symmetric situation, which is better for calculation, which we will call a spin fountain. There are spins injected from here, and then they go up, and then die, and then they produce this electric current, which works as a fountain. The electric current goes up, falls down into the basing, and then flows back over the bottom of the basing, and then goes up again. So indeed, you can find that if you connect the voltage, the voltmeters in different positions here and here and there, the voltages are all different. You can find how they depend on the thickness of the ferromagnetic cover layer here. It's all very interesting, but one important issue is that you can calculate how far the spin accumulation propagate from here, where it's injected, away to the left and to the right. And that's the, any questions? No. And that's the log plot, the log of mu s shown on the vertical line and the distance to the injection point shown on the horizontal plot. What you see is that the spin accumulation drops with a characteristic distance of the spin diffusion lengths in your normal metal. That's exactly what you would expect normally. But then it transfers or changes into another exponential. So there is a tail with a much longer exponential. You can prove that the characteristic length for that extra exponential is the thickness of the ferromagnet, this measurement contact. And you can go even further, and you can see that if you make the upper ferromagnet infinitely thick, then the drop of spin accumulation becomes non-exponential. It's now a power law, which brings you to the following picture. If you inject spins into the normal wire, they decay with the length that is spin diffusion in that wire. If you inject spins into the normal wire and covers this normal wire by a normal metal, then there will be some effective decay lengths, which is a combination of spin diffusions in N1 and N. Now, if you do that, but you cover it with a ferromagnetic layer, then if the layer is infinite, what happens, you create a lot of circular currents. And the circular currents move in ferromagnet and then in normal. And why they move in ferromagnet? They carry spin current with them, because that's what we learned before. And so they bring spin current far, far away and inject it here. And that's how you get non-exponential decay, because now spins don't just diffuse by themselves. They are transported further and further by these electric currents that you have created. And I think I will finish here because, yeah, there probably is no time for a second example. So thank you very much.
Thank you, Professor Bazaliy, for wonderful talk and beautiful effects. We have time for questions, and first one I see from Mykola Bondarenko.
Thank you very much. I have two questions. One is concerning this picture. So was this, I was curious, was this non-exponential decay law experimentally verified?
No, it wasn't verified. It's an interesting experimental problem because, you see, because it's a small signal. It does decay initially here, and that's exponential. So what is left, or where this interesting phenomena are happening, it's already after you got a lot of decay. So it's not easy. It's possible, but you have to do a lot of work.
It's less than micron, the distance.
Yeah, the distance is, you know, when people fabricate them, microns are normal. Anybody can do microns.
Mhm.
It's when you want to do like 100 nanometers or 50 nanometers, that's when you have a difficulty. But even now, you know, you can go and people will do it for you if you talk to them nicely. So it's a possibility.
I also wanted to ask you, could you please comment a bit on how this P realized in practice, which is conductivity polarization?
Yeah, sure. So you look at this picture for a Stoner model for a ferromagnet. There are two bands, and every band has its own density of states, its own Fermi velocity here. So if you substitute it simply in a formula for diffusive conductivity, you'll see that they don't have to be the same. So you have different numbers of particles, but also different mean free paths and different Fermi velocities. All these parameters are decoupled in a ferromagnet.
I was thinking about some more microscopic things. Maybe ions are polarized, so they scatter the electrons differently.
No, even if scattering is symmetric, if it doesn't depend on up and down, you still have simply different bands for them.
Oh, okay, clear. Thank you.
We have another question from Oleg.
Maybe it's not a question, but it's a remark. It seems to me very similar to a problem of superconducting and normal currents in non-equilibrium regions in superconductors. When in non-equilibrium and non-stationary regions like phase slip centers, you have simultaneously two kinds of particles, normal electrons, unpaired, and Cooper pairs, and a different decay length, relaxation length for those two. So you have the difference in mu potentials in chemical potentials. So it resembles somewhat, has some in common here.
I agree that, yes, there is a resemblance. There is one, I'd say, important difference between the two cases, and that's that if you would have superconductor here instead of a ferromagnet, then even if there is no electric current, you're in equilibrium, there is a penetration of superconductivity into the normal metal. And so there is some superconducting properties here, some correlations. In the case of F and N, there is no propagation. There's no injection of extra spin into normal metal in equilibrium.
Mm-hmm.
And what happens in equilibrium is what we know from RKKY interaction. There is a spin wave here in normal metal, which is created by the proximity. But there is no spin accumulation. So the spin, which is, you can say that it is injected, but it's injected at the very large wave vector. And so it oscillates, the spin polarization in normal metal oscillates with the 2K Fermi inside here. But there is no static spin accumulation. And that is the difference. However, there is also another similarity, not with a superconductor, but with semiconductor physics, where you have P and N regions, and you have both particles and holes that live in the same area, and each of them diffuses separately, but you have to maintain electron neutrality. So this so-called bipolar transport, which is a big deal in semiconductors, obviously, is also a very good analogy of what happened here. So in fact, you probably can sort of generalize it incredibly and say that you talk about just any two species of current carriers and their interconversion in a slow way.
Okay, I see. Thank you very much.
Do we have other questions, comments? From my side, could you please comment on applicability of these two current model, maybe from also experimental side? So mainly we saw this hierarchy of paths, right, with collisions and spin flip collisions, but also from a point of view experiment, what are the limitations?
Experimentally, it works very well for a large number of situations. So in experimental metals, they're like normally people grow as structures. These are films with many layers. So they're grown by sputtering or something, and they're not like really very crystalline. There is a lot of momentum scattering. So they are very diffusive. People try to create situations where you have a ballistic regime, but that's very difficult. And mostly that's done in semiconductors where people did it long time before with normal heterostructures for all this long mean free path applications like mesoscopics, quantum Hall and stuff. People tried to have ballistic transport in graphene, but for metallic wires and multi-layers and heterostructures, it usually works very well.
Thank you. If there are no more questions, I would like to thank the speaker on behalf of all participants. And I guess we would also continue with unofficial part announced before the talk, right? So thank you, Yaroslav.
Yeah, thank you everybody for coming, especially those who hear explosions all the time. It's very nice. Thank you.